The purpose of this design is to study the effect of inserting a rectangular extended surface, or what we call fin, to a wall. Our theory states that a fin enhances the rate of heat transfer between the solid and an adjoining fluid. We will test our theory by drawing the fin on ANSYS workbench, setting our boundary conditions, and getting the corresponding results. In order to get the overall heat transfer and the temperature distribution associated to the fin, the following steps will be applied. We first start by dragging the geometry component into the project schematic. The objective is to draw a rectangular fin by extruding a rectangle in a certain thickness. Then, we extrude a larger rectangle on a separate sketch to get the following geometry. Named selections are very important in later analysis, so we right-click on each part, select Named Selections, and name them. The second step is to start meshing by dragging the mesh component into the project schematic. We right-click Mesh in the outline tree to get the Details of Mesh window. In Defaults, we set Physics Preference to CFD and Solver Preference to Fluent. In Sizing, we set Use Advanced Size function to On Proximity and Curvature. We set Relevance Center to Fine, Smoothing to Medium, Transition to Slow, and Span Angle Center to Fine. After multiple trials of mesh generating, we find convenient values for the growth rate and the minimum edge length, which are in this case 1.2 and 1 mm. Inflation is used when we want to increase the precision of the analysis at a certain region. Hence, we set Use Automatic Inflation to all faces in chosen named selections. In our case, we want the mesh to be precise at the fin, so we set the named selections to the fin base and the walls. Then we generate the mesh. Specific values can tell us about the mesh quality. Such values are retrieved from statics in the details of mesh. We set mesh matrix to skewness. Maximum skewness should be less than 0.95, which is the case. Then, we set mesh matrix to orthogonal quality. Minimum orthogonal quality should be more than 0.1, which is also the case. Here we show you different cuts of the mesh. Hence, we move to the next step, which is dragging the fluid component into the project schematic. Different solution setup has to be added in order to run the calculations. We start with General, where we set the solver type to pressure-based, the velocity formulation to absolute, and the time to steady. In models, we can activate different settings. For example, we turn the energy turn on. We can also add the viscous turn, and we set the model to laminar, since, based on the problem conditions and after calculations, the Reynolds number is equal to 3.74 times 10 power 3, which is less than 5 times 10 power 5. In materials, we added the fluid and the solid to the types we want, which are air and aluminum respectively, and we can edit each material to get its properties. Boundary conditions are very important. In our case, the base has a temperature of 343 Kelvin. The inlet fluid has a temperature of 293 Kelvin and a velocity of 2 meters per second. We are using a convective tip. In solution methods, we set the sheen to simple, the gradient to least square cells, the pressure, momentum, and energy to second order. Before running our calculations, we click Solution Initialization to check that everything is good. Then, we click Run Calculations after setting a certain number of iterations, and we wait for the solution to converge. We can observe the convergence of the iterations to the solution by observing the scaled residuals graph. After calculating, we go and check the results. To get the overall heat transfer, we can edit fluxes onto reports, then set total heat transfer rate at the wall of the fin. The answer is a negative value in watts, since heat is transferred from the fin to the surroundings. To get the temperature distribution in the fin, we can edit XY plot under plots and set the y-axis to temperature. Then, under new surface, we choose new line and we insert its coordinate such that it will pass by the center of the fin. A new window appears where we set the coordinates of 2 points passing throughout the line, which are 0, 0, 0 and 0, 1, 0 in our case. The line name appears under surfaces, we select it and we click plot. A plot shows us the temperature distribution versus line length. In results or CFD component, we can also click on contours in the toolbox to get the temperature distribution for base and the fin. After conducting such calculations, we should be able to get the exact value for the efficiency and effectiveness of the fin, plus we are able to compare values taken from ANSYS to our analytical results and get the error percentage.